So I will start with the introduction to the interTwin digital twin engine. We presented already this introduction to the project in our previous webinar, which was in the middle of May, related to the environmental digital twins. But I added more information for those that even if you have attended also that webinar, there are more information about the project and the digital twin engine here. So the project started in September 2022. It runs for 3 years. And basically, the consortium is quite vast. We have 30 participants with different capabilities, providing, for instance, either resources that are needed for the piloting or developing some technologies, so they're technology providers, or and the big chunk of our community, our project participants are representative of communities from different fine domains, which we'll present later. In particular, I wanted to share that all the providers in the project provide different type of resources: cloud, HPC, and HPC. Some of them, like both of them. So we are trying to reuse as much as possible hybrid solutions on the infrastructure, and of course, it's coordinated by the AGI Foundation. Just to start with the, given that we are developing a digital twin engine, I would like to introduce what we define as digital twin. There are many and different definitions for the digital twin. The one that we have reused in the project is defining the digital twin as a virtual representation of a physical object, process, or system, which is created and sustained with information derived from one or many data sources, which could be like models or sensors, and also considering historical and real-time observation. This definition is coming also from known glossaries, for instance, the one that is being developed by the Digital Twin Consortium. So we are trying to align to what is defined there. You can find, for instance, if you browse this Digital Consortium glossary, the definition of digital twins of the related systems. Recently, I also included here a link. One of the partners in the project, the Deltares, also started prepared a white paper about digital twins, also defining what are the different types of digital twins that are out there. In particular, you can find, for instance, in the industry for cities or airports and environment, which is one of the domains that we are covering here for different goals with different system representation time span, which I put it in this slide. So if you go to this link, you can see also this white paper, which is quite interesting. So the interTwin digital twin engine is mainly for scientific purposes, and is co-designed together with many use cases from physics and environmental science. The resulting platform is based on open source technologies and open standard. We are targeting mainly 2 categories of users. So from one side, we target developers, which have knowledge of the system and develops digital twins using the modules that we are providing in the digital twin engine, which I will describe later in more details. And then we target also end users, which in our case as data scientists or policymakers, which of course they interact directly with the digital twins that are being developed. The project, as I said, started in September 2022. We had a first year that was dedicated mainly for the design and specification, requirement gathering, and the first deliverable that were related to the specification of the system and the applications, the DT application, the design, and then of course during the last part of the year, the development started, and we have a project here too, the first software release of the platform. And during the 2024, we continue all the developments, and we released also an updated architectural document. And recently, we released also the first deliverables and the first version of the digital twin application, which are integrated part of the functionality that were developed during the first year of the project. We are now working on updating the design and specification of the system, while the project year 3 will be mainly dedicated to the final release of the various components, and then the final release of digital twins, which will integrate with all the final functionalities that will be delivered during the second final release. The components that we are developing are divided mainly in 3 layers. So on the bottom, we have an infrastructure layer, which of course includes the hardware. As I said, we are piloting with different type of infrastructure, HPC cloud, and data, of course, repositories. And then we have a layer of components which are federating compute data and also provide the orchestration of the services on top of the hybrid infrastructure. Then we have a layer of core modules, which are, let's say, horizontal to different capabilities that are being implemented for the digital twins. So we have modules for quality verification, workflow composition, particular big data, AI/ML, and data fusion, and then capabilities for real-time data acquisition and processing. And we have a layer of thematic modules which are tailored to the needs of a different digital twin application, which in our case, in the project, we have environmental science and physics, which are divided in high-energy physics, gravitational wave astrophysics, and astronomy. But also, of course, this thematic layer can include also modules from other scientists. And then we have a digital twin application that are basically integrating what's provided at core infrastructure level together with the development of thematic modules. The use cases that we support, that, as I said, are divided into main areas. We have from one side the environmental scientists. So in particular here, we put some of the different use cases that we are supporting for tropical cyclone detection, early warning of extreme events, wildfires, and regeneration, extreme events impacts, which, as I said, have been presented in the webinar in May. Today, we will focus on the bottom use cases, so the one from astronomy, which I presented before. So the Max Planck lattice QTT from CNRS, SIC, and TSZ, the Virgo noise detector digital twins from NFN, and the particle detector digital twin from CERN and CNRS. The benefit of this approach, so in having interdisciplinary, are many. So, for instance, we increase cross-community development and collaboration. So try to break it down silos of the different frameworks that are used. We try to use also the DT, as I said before, try to be infrastructure agnostic. So it's going to be used and run in different cloud and HPC center in Europe. And the modularity and extensibility are also demonstrated because we can provide support for new use cases, and we can customize the various service according to the specific use case needs. What I mentioned before is that we have released at the beginning of the 2024 a first version of the digital twin engine, which is available on our website, the description of all the different components and their maturity. We have in total 30 components which compose this engine, and we have components developed from scratch, but also components that extend existing software, which I also will mention later. And sorry, I wanted to mention that we have our GitHub organization, which hosts most of the components that have been developed from scratch. So going a little bit more in details, for the core components, which I wanted to describe today. So as I said, we have components for automated digital twin validation in connection with workflow provenance, which are using existing software and extending them, like the SQS platform from EOS Energy. The components for distributed data analysis embedded with specific workflow tools, which extend the functionality of existing software like OpenEO, Ophidia, using Stack Catalog, and also composition of the deployment of overflow using Airflow. And then we have software for real-time data processing connected with the serverless platform, which are using and extending software like Oscar or Apache Nifi. For the big data analytics, we define standardized deployment tools for the big data analytics using Tosca and Ansible. And for all the part related to the generic to the AI ML, there is a new development has been developed from scratch between AI, which is support for the management of the generic workflow for AI AML and model validation. While for the infrastructure components, which a little bit more in detail here, so we have components for the deployment of services using also AI ML to find the best deployment strategies. And for the federated compute, as I said, we want to federate different type of computing and backend. There is a possibility to enable complex simulation and modeling tasks to different computing facilities. In particular, we have also implemented the components transparent of float task to HPCs. While all the part of the data management is based on what has been developed in the Escape data lake. So having components like rules, FTS, and storages which are caching via HTTP. One of the achievements that we had so far in the project, apart from the development of the different components, is the architecture blueprint, which is available also in Zenodo. We have a second version developed at the beginning of the year and a final one at the end of 2024. And this blueprint also considers other initiatives and projects which to understand also architectural components that can be incorporated with the interTwin, or where we should where is needed to have interoperability. One of these initiatives is the Destination Earth. So we have, in particular, in interTwin, we have is in WF as a partner, which basically help so far the project to design a compatible architecture with addressing also the requirements of a large set of user communities. We plan for the end of the project, and we are designing now piloting activities, in particular not for the digital twins that you will see today, but for the ones that are related to extremes and climate. Now that this national, which is the major, let's say, initiative for the digital twin of the Earth, has been open to users only like 2 weeks ago. So just for concluding this my first part, I would like to say that we concluded the process of co-designing the platform and the blueprint architecture, the component definition, together with the member of the user communities. We had the first release available of the software, which included components also available in our GitHub. We have like several pilots running on infrastructure, and we integrated the use cases now with the first deliverables in May. And we aim to complete the developments of the different components in January. And of course, we would like to engage also with external communities, and not only with the one that are use cases in the project. And the final goal for us is to extend and operate the detection engine after the end of the project as one of the services that will be provided by the AGI Federation. So this is concluding my introduction to the project and the digital twin engine. As I said, if you have questions, you can put it in the Q&A. If there are now questions, I can reply. Otherwise, we will see it later at the end of the webinar. I don't see now questions for this first part, so I can leave the floor now to Kalliopi for the digital twin implemented by CERN. I stop sharing, so Kalliopi can.
Thank you, Andrea. I'm sharing the screen. Okay, can you see my screen? Is that okay?
We don't see now. Now it's okay.
Okay, awesome. So thank you, Andrea, for the introduction, and hello everyone and welcome. My name is Kalliopi Tsolaki, and I'm working at the interTwin project. on the support and development of the CERN use case. I'll present to you today the digital twin we are building for fast particle detector simulation and its progress so far. CERN is collaborating with scientists from the Physics Institute of CNRS, the French National Center for Scientific Research. Before I dive into the digital twin and what is it about, I thought that it would be interesting to start with an overview of LHC, WLCG, and other background concepts, which will smoothly lead us to the relevance of the digital twin we are implementing. By now, you may have heard that the Large Hadron Collider is the world's largest and most powerful particle accelerator. It's a 27-kilometer ring of superconducting magnets, where two high-energy particle beams travel at close to the speed of light in opposite directions, and before, of course, they are made to collide. Beams inside LHC collide at 4 locations around the ring, which are the positions of the 4 experiments, where the 4 biggest particle detectors reside. I mentioned detectors. Detectors are actually devices that gather information and data about the particles, like their speed, mass, and charge, from which physicists can work out a particle's identity. What is then a detector simulation? Simulation of particle transport through matter is fundamental for interpreting the results of high-energy physical experiments. Particles undergo complex interactions while traveling the detector material with stochastic outcomes. These processes are modeled with Monte Carlo techniques that rely on repeated random sampling. And Monte Carlo simulation meets the theoretical predictions with a high degree of precision, but is usually time and resource intensive. An important fact here is that the worldwide LHC grid, which is actually a cluster of global computing resources for the storage, distribution, and analysis of the data generated by the LHC, is currently using more than 50% of its resources only to simulations. Also, the luminosity upgrade project of the LHC has been measuring that this upgrade will require 100 times more simulated data. Now, moving forward, let's see how the detector simulations that I'm talking about are performed. Scientists are using the GN4 toolkit. There are other toolkits as well for this purpose. It is an open source tool that enables simulating particle passage through matter. Toolkit means that there is no main program provided when you want to build a simulation application, but it provides all the necessary components needed to describe and to solve particle transport simulation problems in the form of user interfaces. Basically, it provides the necessary tools to the users to write their simulation applications. It includes interfaces for defining and describing the problem, depending on the specific context that the scientist is trying to solve, such as interfaces for describing the geometry of the detector, in this case, meaning the volume, shapes, sizes, and materials. Also interfaces describing the particles that are passing and their properties, as well as the underlying physics that govern such applications. In addition, for the described problem, GN4 provides the solution interfaces, meaning the step-by-step particle transport computations based on Monte Carlo methods. The challenges of particle detector simulations in high-energy physics is also our motivation driving this work and the work in interTwin project. The detailed particle Monte Carlo simulation we talked previously is inherently slow and consists a complex multidimensional problem. These simulations have a crucial role in high-energy physics, experiments, and at the same time are very resource intensive from the computing perspective. Computing detector simulations allow scientists to design detectors and perform physics analysis. At the same time, there are parts of the detectors, the so-called calorimeters, which are measuring the energy of particles passing through the detectors, and which are the most time-consuming part while simulating the passage through them. Therefore, the high-energy physics community is highly motivated to explore fast alternatives, often trading some accuracy performance for speed. Basically, fast simulation is a set of established techniques that replaces parts of the detailed Monte Carlo simulation with alternative approaches. By fast simulation, we are referring to a set of established techniques that replace parts of the detailed Monte Carlo simulations with alternative approaches, including generative approaches like deep generative models. For our digital twin of a fast particle detector simulation, we are leveraging a generative adversarial network approach, which has already shown promising performance as a standalone application. The GAN approach that we are leveraging has already been utilized. No, excuse me. Here I wanted to mention that GAN, generative adversarial approaches, have already been utilized across different other high-energy physics experiments for the same purposes. Moving forward, so our goal is developing a data-driven actual digital twin that simulates particle detector response and integrates operation conditions from experimental setups. So how we are modeling this problem? Detectors can be described as 3D cameras taking pictures of particle collisions. The calorimeters, as we said before, detect particles by measuring the energy deposited when those particles interact with the detector materials. The calorimeters also consist of arrays of active sensor material and passive dense layers, and that ensure that the incoming primary particle will deposit most of its energy inside their volume. In addition, the energy depositions in the calorimeter cells can be represented as monochromatic pixel intensities of a 3D image. Therefore, the problem is now formulated as an image generation task, which can be tackled by using deep learning. Now, let me walk you through the activities performed so far in order to build a digital twin for a fast particle detector simulation. This involved the DT application design and its capabilities. In high level, our digital twin has two inseparable components, the simulation component and the deep learning component, which replaces specified parts of the simulation process. On this end, we've identified the technical requirements of such a digital twin, and we've selected the detector use case representing current challenges, which is the calorimeter case, as those subdetectors require the largest computing resources for simulation. We also identified and designed user stories that define the key functionalities and requirements, which were reported in the related project deliverables. Finally, we have reported the first version of our digital twins capabilities in their respective deliverable that is publicly available. Regarding now the development of the generative model component of the fast particle detector simulation, we have designed the work plan as follows. To optimize, we started to optimize the deep learning network developed for a selected set of detector geometries. And we want to integrate tools for distributed training and hyperparameter optimization, and to implement the validation techniques capable of assessing different performance model aspects. As already mentioned, since Monte Carlo processes are highly demanding and computing in time and computing resources, the alternative we are leveraging is a generative adversarial network. The advantage of actually leveraging a generative model is the ability that the generative models have to generate directly the detector output without reproducing step by step each single particle that interacts with the detector material. Our GAN approach is built on specific detector setup and is trained to provide images similar to the ones that are produced by Monte Carlo methods. Moving forward, we have based our approach on a prototype called 3D GAN and has been built to simulate a future high granularity calorimeter output as three-dimensional images. It has been proven to speed up the particle generation process of 3 orders of magnitude with respect to the traditional methods. As the calorimeter detectors consist of layers of cells, those cells are modeled, as I mentioned also before, as pixelated images, with the cell energy depositions being the pixel intensities, essentially. Our GAN model consists of 2 networks, a generator and a discriminator. Each network is trained using 3-dimensional convolution layers to represent the 3 spatial dimensions of the calorimeter images. And in the image on your right, here is an example of a shower, as it is called, of particles created by GM4 on the left and by the GAN model on the right. And this actually shows how well the network can be trained to produce very similar data representations from the same initial conditions. Through the process of defining how our application for the fast detector simulation will work, and in order to identify the software components we need to build to achieve this, we have broke down the basic workflow into 2 separate workflows based on the capabilities each one includes. As for the first development phases, we started building the training workflow, which briefly works as follows. We use data produced by Monte Carlo-based simulations and which are based on a detector-specific configuration. The produced data consists of the energies measured by the calorimeter sensors, the properties of the initial particle, such as its type, energy, and the trajectory angle with respect to the detector volume, and other metadata. The data produced from the traditional Monte Carlo simulation are by default in root format. Root is an open source data analysis framework used in high energy physics. And those data require conversion into another format, the HDF5 format, which is another data format designed to store and organize large amounts of data. This conversion is required before data are fed into the generative model, and then we train the model on the pre-processed data. The model is conditioned on specific input that describes particle properties. Next step we are currently working on is to add the model performance validation. The model generated data and the original GM4 simulated data distributions will be visualized. And at the end of the training workflow, the optimized models selected based on the validation results will be saved. The second phase of development involves the inference workflow. During inference, the GAN model generates 3D images replicating the original calorimeter images. Finally, based on the results visualized, 2 possible workflows are proposed for calorimeter simulation tuning. The GAN model can be either re-inferred with different model input parameter values, provided these parameter values have been accounted for during model training, or alternatively, if a different value range of the conditional parameters is needed, the training workflow must be rerun from the beginning. These two possible workflows allow actually for greater flexibility and adaptability in tuning the detector's response to various particle interactions. In the next slide here, you can see the CERN detector, the actual CERN detector on which we've based the configuration of our model, and more specifically, the model is based on the calorimeter subdetector included in the click detector setup. The development of the model is complete, and also the first version of our digital twin of the calorimeter, since it can generate 3D images of particle interactions similar to the images that the physical detector can produce. Currently, we are focusing our work to include the performance validation capabilities, which will create data distribution plots of the generated data and the original training data for comparisons. And here on the right, you can have a look on the first analysis results obtained from a very initial version of the prototype. Since the development of the calorimeter digital twin, which includes the 3D GAN module, reached its first release, we have also held different integration activities with the interTwin digital twin engine modules. For example, loading and preprocessing of our data, training and testing of the 3D GAN process have been integrated with the AI workflow framework called iTwin AI. Inference has also been integrated with the workflow execution tool, the OSCAR, again, using and through iTwin AI framework, and integration activities with SQAS services for software quality assessment have been also performed. And for more detailed description on the integration of the different digital twin engine tools, you can follow the demo curated by the respective colleagues, and you can find in our interTwin YouTube channel. Now, wrapping it up about CERN's digital twin development, I will give an overview of our future steps. We'll be working on exploring the integration of the GAN models to the Monte Carlo-based framework, GAN4, which will strongly depend on the level of support from the project's infrastructure, though it is not something necessary for the completion of our digital twin, since the modules already developed are already working and performing as a digital twin of a particle detector. We will optimize the data transformation pipelines. We are planning to develop or integrate tools for parallel training and hyperparameter optimization. Those tools need to be, we will need to best adapt them to specific use cases. Also, we'll continue working on the development of a validation framework in collaboration with high-energy physics community experts, which will be based on validation techniques capable of assessing different aspects of performance. And finally, we will work on integration and test compliance of our software components with the digital twin engine solutions developed. Thank you. This brings me to the end, and thank you for your attention, and I'm available for questions and or comments.
Thanks a lot, Kalliopi. I see one question on the chat about from Sai. Sorry, to use your name, I guess. Can we use diffusion model instead of GAN for a deep learning model? This is one question.
Yeah, technically we could use it, but it needs to be in it needs to be adapted on the specific detector setup that we have built. But if it is a diffusion model developed for a specific detector setup, yes, it can be can work as a digital twin of a particle detector with the correct validation aspects.
Also, see another question about workflow in slide 25.
Now, let me share maybe again.
Well, I mean, we do a webinar for questions, so otherwise.
Slide 25 here. No, maybe here.
So the question is about the gun that you are using to generate static data. Can you elaborate also on the deep learning method employed in your approach to create data-driven model, and what is your final target?
To create the data, the triggering. Are they asking about the triggering process? Can I also see the question?
Do you see the question on the chat?
The one for the LHC experiments, right? Or maybe I'm not seeing the correct question, but
No, there is on the chat, not on the QA, the question. You know, if you see the chat.
sorry. Okay, so okay, so actually the data that we used for training the GAN model are generated with the GN4 simulation toolkit I talked before. And we used those data actually to train the generative adversarial network that we are employing for this work. I think that this should answer the question. And for the final target, the target is that we are able to create images similar to the ones that can be produced from the Monte Carlo, and simulations actually that can be produced from the Monte Carlo GM4 framework more efficiently.
Yeah. Is that okay, Faride? This is to answer your question. Okay, thanks a lot. Okay, I see also another question on QA. Given that we are running a little bit late, if maybe you can reply directly there on the chat of the QA. Thanks to Kalliopi. I think we can move to Lorenzo now. We have allocated 1 hour and a half for this webinar, so we should be able to to manage to finish in at 3:30.
Okay, sure. I'll go fast then. Let me share my screen.
Yeah.
Can you all see it? Let me just. Okay. So hi everyone. I am Lorenzo. I am working on the Virgo gravitational wave interferometer digital twin.
Can you, Lorenzo, sorry, can you please speak close to the mic, because
sure.
we are...
Sorry. I've been having some mic issues. I hope this is better. And so I will presenting you the Virgo interferometer digital twin today. I will try to do that in the most simple way as possible, so that even non-physicists or non-experts in general can follow and understand what's going on. The talk today is structured in 3 main blocks, in which I'll address 3 very basic questions. These are: why building a digital twin of the gravitational wave interferometer? What is a digital twin of the gravitational wave interferometer, and how we actually built it? This slide is sort of a 30-second version of the presentation, and it's the take-home message. So as for why, we we know that gravitational waves interferometers are important because they allow scientists to detect and study gravitational waves, which help us understand the universe and uncover what is left for us to do in theoretical physics, as part of it at least. But the gravitational wave interferometer sensitivity is limited by noise. So we want to find a way to separate physical information from the noise in the data. And we do that making use of generative models because neural networks in general have this encoded ability in themselves to learn a linear structure in the data and therefore cannot perform standard analysis tools. So let me start telling you a bit more about why we do things. So gravitational waves are ripples in the fabric of space and time. And you can imagine space as a huge, stretchy, rubbery sheet. And whenever heavy objects like stars, black holes, whatever, move and accelerate, they create waves on this sheet, similar to how a stone dropped in water creates water ripples and waves. And these waves, in the case of celestial bodies, are called gravitational waves. And even though their existence was predicted over a century ago by Einstein's famous theory of general relativity, they were not directly observed until September of 2015 by the LIGO-Virgo collaboration. You may say, okay, cool, but why do we care about gravitational waves? Gravitational waves are important for these main three topics, which I'll show better in the next slide. I was saying they are important because they open a new window to the universe. Traditional astronomy relies on light and electromagnetic radiation in general to study celestial objects, but light can be blocked or absorbed by dust and gas in the galaxy, in the universe, and therefore the information that we obtain by light can be partially obscured. While gravitational waves, on the other hand, they pass through everything, so they provide a clear signal even from the most hidden parts of the universe. So by studying gravitational waves, scientists, what can they do? They can observe new phenomena, because some phenomena they don't emit in the other spectra, or are not occluded by our sight. And they can also learn more about the already observable phenomena, as the gravitational waves carry different type of information from the other types of messengers. And the combination of the observation in different part of spectra, the light, the gravitational, etc., is called multi-messenger astronomy, and is one of the hot topics in physics now. Furthermore, scientists can gain insight into the early moments of the universe, potentially confirming or refining our understanding of the Big Bang. And lastly, they can give us, they can test some fundamental theories of physics, like Einstein's theory of general relativity. Those theories can be tested into extreme conditions that were not tested before, and ultimately, maybe the testing of these theories will lead to the development and the formulation of a new theory of quantum gravity, which is one of the biggest challenges left in theoretical physics. So I hope that now it's sort of clear why we need to observe gravitational waves. Let's see how we actually do that. And to do that, we need very complicated objects that are called gravitational wave interferometers. And to understand how these things work, imagine just that you have two identical rulers placed far apart from each other. And if a gravitational wave passes, remember it's a ripple of space-time stretching and squeezing of the fabric of space-time. Whenever it passes, then the rulers will be slightly stretched or squeezed. So by looking at these rulers and seeing how their size changes, we're able to measure the passage of a gravitational wave. And gravitational wave interferometers are more sophisticated version of this idea, by using light to measure these incredibly tiny changes in the distance of the rulers. In fact, at the heart of the gravitational interferometers, there is a powerful laser This laser is split into two beams that are made travel down along these two perpendicular arms, very long, in the order of kilometers. They are reflected by mirrors, and then they are recombined and ultimately sent to a detector for analysis. As if the lasers travel the same distance in the two arms, the phase of the two beams, when recombined, will be the same. But if a gravitational wave happens to be passing by, it might be that one of the two arms gets stretched or squeezed a bit, and therefore the laser has to travel a longer or shorter distance, respectively, with respect to its other half. This will cause the phase of the beam to change. So when we recombine the beams, by measuring this phase difference, we get to measure these tiny stretches and squeezes of the fabric of space-time. And therefore, we know that a gravitational wave was passing by. Of course, a real gravitational wave interferometer is much more complicated than the thing I've just described. And having to measure incredibly small variations in the length of the arms, it must, of course, be sensitive to a lot of other tiny fluctuations that come, of course, from multiple sources of noise. You can see some listed in the slides of environmental nature, like wind, seismic noise, the weather, sea. Think about that. Virgo is about 30 kilometers away from the coastline, and yet when there is an increase in this sea activity, it picks it up. So it's very, very, very sensitive. Then there are other sources, and even some crazy ones that you wouldn't think about it, like planes in the sky and people sneezing. Of course, with the sneezing, I'm joking, but planes in the sky is actually true. You can see an email from the DETCHAR team from about a month ago, where basically they were alerting the fact that a helicopter of the police was flying over the site of the interferometer, and this was picked up by the interferometer. So in order to control and keep track of all of these sources of noise, on top of the channel measuring this variation in phase that I was describing, there are a lot of control channels to monitor the status of the interferometer. In Virgo, they are of the order of 100,000. And this data is used to make corrections and to subtract noise from the data, but yet the data is still buried under the noise. So now that we know why we need to do those things, let's see what we want to do. There is a particular type of noise that we are concerned with, which is called a non-Gaussian transient noise. It's commonly called glitches, which is one of the most single challenging limitations in the study of the gravitational wave interferometer due to its similarity with astrophysical sources signals in the time and frequency domain. In other words, this means that we have a particular type of noise that actually looks like the signal. And this is very problematic, as you may think. Therefore, we need to explore novel methods to recover physical information from the data corrupted by glitches. And in our work, we focus on modeling and generating glitches using deep generative algorithms. And the strategy involves mapping glitches from carefully chosen auxiliary channels, which are the ones that measure the seismic activity, etc., etc. And those channels have to be uncorrelated with the physical signals because we don't want them to pick up gravitational waves, of course. And we map them to the strain or main channel of the interferometer. And this allows us to subtract the generated noise from the physical interesting data and leave us with the clean data. And the edge that we gain in choosing deep learning for this task is that, as opposed to traditional signal analysis methods, it naturally deals with nonlinearity relationships in the data, which is crucial for our task. And to help the model learn better and faster, we make use of spectrograms, which are the images you see at the bottom of the slides, which are nothing but visual representations of the spectrum of frequency of the signals as they vary with time. So it's the frequency and energetic content of the signal as a function of time. Time is on the x-axis and on the horizontal axis, while the frequency is on the vertical axis. So how did we do things? So the first question that we needed to answer is which channels should we use to build the detector? One could just say, let's use them all, but there are 100,000. So it's impossible, not feasible. So the first thing we did was building this Analisa tool model, which is nothing but a tool for finding correlations among channels. So we want to find the channels that are witness of these glitches. And our idea was to define the degree of correlation between two spectrograms via the number of common peaks among the channels. And by common peak, we mean a peak above the intensity threshold occurring at the same time. And the correlation coefficient can be calculated simply as the ratio between the number of common peaks and the number of peaks in the strain channel. Note that this definition allows us to capture nonlinear relationships in the data, as we allow common peaks to have different frequencies. And so we used this tool to scan through all the glitches for a particular type of glitch, which is called scattered light, which is basically due to some seismic activity. And we used the data from the Virgo interferometer in the previous observer run, not the one that is currently happening right now. You can find the code and all the documentation for this tool at the link in the slide. And this Analisa tool is inserted into a bigger picture for the digital twin engine thematic module for the Virgo use case that you can see in the slide. So it is used only once at the beginning of the training, for instance, at the start of each observing run, because the interferometer setup can change a little. So what we do, we scan all the available data set we can find from the interferometer, we select the relevant channels, and we feed it to the actual digital twin. The digital twin is made up of two main components, one training submodule and one inference submodule. And the selected data is first fed into after the Analisa selection, it is fed into the training submodule, where the data is fed to the preprocess API, which basically cleans the data from like static sources of noise and does some standard preprocessing to just cast the data into the correct format for the train to work with, for the model to work with for the training. The preprocessed data is fed into the glitch flow module, which is the main module of the digital twin, which is basically a module for training a set of generative neural networks. And then once the model has been trained, it is stored in the model catalog and then uploaded onto the generative API, which is then used for inference. And let's say the way the modules interact is all mediated by Airflow, and the way they put together. And all of the code and documentation can be found at the link in the slide. And the single submodules are part of the first release that Andrea was talking about at the beginning of the presentation. Let's now dig a bit deeper into the glitch flow, the main component. As I was saying, is just a collection of neural networks. Here you can see we have used for this generative task few very simple decoder and encoder-decoder architectures. We've used as the loss for training a simple L1 loss for the sake of simplicity and robustness of layers. And the type of data that we've used is a couple of auxiliary channels. We computed their spectrograms, and we fed into the network these two auxiliary channels and the main channels as a reference for training. The results of training can be seen in this slide. As you can see from the loss in the top left of the slide, the model learns very fast and starts to introduce bias after a few epochs. It means that it learns to generalize well the outliers in the training set, but fails to do so in the test set. We kind of expected this because we are just using a couple of auxiliary channels, so it's not worrying us. And we are confident that increasing the size of the data set and the number of channels will fix this problem. As for the results itself, you can see in the slide a good example and a bad example. Most of the results are belong to the first category, luckily. So most of the results are good, and some of the good results are actually very, very good, like the one you can see in the slide, where the glitch is actually completely picked up by the network and removed safely. And the bad ones are a few, and they happen whenever the input is messy or odd looking, meaning that it's very likely that those two auxiliary channels are not enough to fully describe this category of glitch that we are analyzing, and therefore we can fix this problem very likely by increasing number of channels in the data set. Let's give you a bit more of a qualitative description of the performance of this model. Let me remind you that we have a twofold goal, which is first of all generating synthetic glitches in order to subtract them from the interferometer to perform vetoing task. So this means checking if the excess in energy that we see in the main channel is due to a glitch. And then there is a second task, which is the denoising task, which is precisely removing the glitch from the interferometer, clean the data, and use the clean data for further analysis. And to keep track of these tasks, we've come up with a set of custom accuracy metrics that mimic the actual alert trigger mechanism in place in the Virgo pipeline. It's a software called Omicron that I will not, I mean, it's over the scope of this talk, but oversimplifying just computes the Q-plots of the data, cluster the glitches as areas in Q-plots where there is an excess of energy. It means those yellow blobs you can see in the slide. And after the clustering, it sends alerts according to some threshold levels. In other words, if the yellow area is yellow enough, it sends an alert. For the vetoing task, we have monitored whether the model does indeed generate glitches from the auxiliary data, if and only if there is also glitch in the corresponding main channel data, and if the generated glitch has the correct time frequency content. This means that the yellowish blobs that I showed you in the previous slide have the right shape and the right coordinates in the image. And you can see in the number in the slide, this task is nailed by the model as the glitch accuracy generation is stunning, and so is the position accuracy for the medium and high level alert. There is still some fixing to do with the low level alert, but these are very, very, very good results. The same cannot be said, unfortunately, for the denoising task, but we expected this again because we've used only 2 channels. And in this task, we have tried to subtract the generated data from the corresponding real data from the main channel, and then checked if the result was still a glitch. And so this means checking whether the generated yellowish blobs actually have the correct shade of yellow. Unfortunately, at this stage, the model is not able to do this task, to perform it well. But as I was saying, we're confident that with an increase in the number of channels used and in the dataset used, we will be able to tackle this. So to wrap it up, are the next steps. So these are some more technical aspects that I didn't really cover in the presentation, but basically we need to improve our Analysa tool in order to make the scan faster. So we need basically to move the computation of the spectrograms to the GPU, and to do that we need to develop some code for this. And then, of course, we need to perform the analysis in a bigger data set for all channels, because for now we just did that over a small subset of channels. This is why we only have 2. And once we found the new channels, we can retrain the network and improve the performances. And then we also need to finalize the generative API module, as well as fixing the user interface and the way the airflow DACs are set up in order to make the various submodules communicate. And I guess that is all from me, and thank you for your attention.
Thanks a lot, Lorenzo. I don't know if there are questions from the audience. I don't see it from the Q&A. But you can also write it and then do it later. I mean, at the end, not an issue if you don't have questions immediately. Well, given that I are a bit late, I would like to continue then. And so thanks again, Lorenzo. And we switch to Yuri.
Okay, can you see my screen?
Yes.
Okay. Okay, so my name is Yuri Pitoprihara, and I'm presenting the radio astronomy use case. You probably all know what radio astronomy is a field of observational astronomy that studies various cosmic phenomena at radio frequencies. And its areas of interest range from objects of our solar system through all kinds of stellar events in the galaxy to studying various galaxies and up to studying the afterglow of the Big Bang itself. Because it covers an enormous range of wavelengths, basically from our normal telecommunication range of megahertz to upper microwave ranging with infrared. You can always find a window where you can see something that you cannot see in any other range of electromagnetic spectrum. So that's why radio astronomy is very important for studying the astrophysical phenomena. What you see here in the image is the traditional radio telescope. It's the one operated by our institute here in Bonn. It's a 100-meter parabolic dish, which was built about 50 years ago, well, more than 50 years ago now. Many times upgraded, of course, but still it's in the old school radio telescope. And what we are coming to now is that we are changing the paradigm of radio astronomy and building telescopes based on completely new technological base. Well, one of the important things in radio astronomy that in radio you can easily do the trick of interferometry. Basically, you can connect many dishes together so they act in phase as one telescope. So, and you can do this even in the scale of the whole planet Earth. So you can basically construct a network of telescopes that acts as a telescope of the size of the whole planet. Now we are switching to these new types of telescopes based on interferometry, and as you can see here in a image, that's an artist's impression of how the SKA gonna look like. SKA is a square kilometer array, which means exactly what it says. That's total area, total collecting area of about a square kilometer, which is enormous. These tools are gonna be superior in every aspect to the older, these parabolic dishes. They're faster, larger, sensitive. They're gonna have many beams that can together observe at the same time in different points in the sky. And so unfortunately, this sort of technological revolution also translates into getting much more data. And the problem with this is that traditionally in radio astronomy, we use the principle of that all the data is sacred, basically because getting the data was so difficult that most of it was kept indefinitely. You can still access archives of data and look into something that was observed in the 80s, for example. And it wasn't a problem because in actual numbers in like megabytes, and it wasn't that much. But now with these new types of telescopes, we are crossing the threshold where we cannot not only keep it indefinitely, we cannot even keep it for a reasonable time for human experts to deal with it. And so we are forced to develop automated methods, automated expert system that would help us to sort through the data and process it. And of course, because of the volumes of the data involved, these tools that we construct must be high performance computing capable, and because otherwise it wouldn't be so. And that's another problem, because traditionally all the radio astronomy software was built for ordinary computers and was run by basically at somebody's desk, just on an ordinary workstation. So these are two things that we are now forced to deal with in radio astronomy. But since we have to solve this problem, we can also see the good side of it. So we can, building these automated systems, we can use them for automated searches of something which is difficult to detect in traditional way. For example, as you can see here in this illustration, something that's called fast radio bursts. These are transient phenomena which just emitted randomly different points in the sky, and they're very difficult to study because it's impossible to predict where you can detect one. And so we're using an automated search with an automated expert system. You can look at like scan part of the sky, and whenever you detect a flash like that, the system would stop and enact some sort of a protocol, possibly connecting other telescopes and in other ranges, and this way, hopefully, the mystery of these bursts will be finally solved. Because at this point, we have only hypotheses; we don't really know what they mean. So this is basically the positive side of this sort of technological revolution that we have to deal with. So this is how the three focus points of our use case come by. So we are trying to develop an automated expert system that can deal with large volumes of data from telescopes in either real time or close to real time, because there is always some sort of downtime. So you can, if you can process it even a bit later, then it's still fine. Then make sure that it's HPC capable, and design it with transient searches in mind. Of course, since transients are unpredictable, you can't really use them for development and testing purposes. So instead, we do this pilot project with pulsars. So pulsars, they also emit pulses, but at regular intervals. So this is what a typical, well, that's probably the most famous pulsar, the crab pulsar, one of the strongest in the sky. What it looks like. So what it is, it's just a rotating neutron star, which is, you can imagine, just as a little ball. It's just about 10 kilometers in diameter. So it has hot spots on its poles, and so when it rotates, it just periodically flashes a beam of radio emission at us, and that's why we see these sharp pulses, and then there is nothing, and then again pulsing at very regular intervals. So how do you approach this? Well, first of all, the name of our project is MLPPA, which stands for Machine Learning-Based Pipeline for Pulsar Analysis. How do we approach this? We have basically two parts. One is the expert system itself. In this case, it's CNN neural network based. So it just assesses the data and assigns labels to each fragment of it. And the other part is the digital twin. It's, of course, the expert system can also be trained on real data, but in a moment I'm gonna tell you why we need digital twin to do it. And the project itself is split into 3 parts. One is empirical part where we study the actual data from pulsars and build empirical models of it and train the classifier to label it and so on. The other is a theoretical block, which builds the physical model for the digital twin. And finally, there is a high performance development block where everything is rewritten in C++ and then tested on HPC clusters and made sure that it works reliably and at high speed. So the digital twin itself, it's a sophisticated physical model of a system of pulsar interstellar medium telescopes. So basically we start with building a neutron star model, how it emits the radio beam, and then how the radio emission is propagated through the interstellar medium, what happens to it. Then we add different kinds of terrestrial, both human-made and natural sources that provide interference. That's usually a big problem for radio astronomy, all kinds of interference with the observations. And finally, model how it's detected by the antenna and the electronics of the telescope. So as our data is, of course, it's when it's coming to antenna, it's just a time series. But for the analysis purposes, it's convenient to split it into what we call time frames, which are little bits of data which have been Fourier transformed. So each one is presented as a 2D image with 2 axes, time and frequency. Here there are examples of this. The left uppermost one is just when there is nothing. So here you see just different sensitivity values for the electronics of the telescope. Then in the next one, which is marked BB RFI, standing for broadband RFI, you see something like, for example, it can be a thunderstorm, or the broad band in all frequencies, you see some sort of interference. Then there are a narrow band RFI, which are limited only to certain frequencies, which are typically related to telecommunications or something else human-made. And finally, you see this slightly curved path, diagonal path of an actual pulse coming from an astrophysical source. And you can see another one, just the better shown one in the panel at the right. The reason for this is the dispersion of interstellar medium. So different frequencies arrive at different time. And this allows us to tell immediately when we deal with the astrophysical source. So using these 2D images as an input for the pipeline, we can much easier train the machine learning component, because the machine learning technology is well developed for studying images, actually. So why do we need a digital twin? Why can't we just use the normal data? So again, you see here the examples of the time frames, various ones. There is another example, mixed time frames. They can combine 2 components like the pulse and interference. And the diagram at the right shows that the distribution is extremely unequal. So in like about 95% of cases, the time frame would be empty. There will be nothing there. In the rest, most of it would be different types of RFI. And only slightly, less than 1%, 0.1%, 0.2%, something like that, would be the actual pulses, the scientific data that we are interested in. So if we use this for training, then our expert system would be extremely biased towards empty frames and various types of RFI. And we want it to be equal. So with a digital twin, you can generate these equal numbers of each type, and then train it this way. This shows already the results of training and then running it on actual data, and you can see that even with the rather low resolution time frames, like 64 by 64, you get pretty good results on the real data after training it was a digital twin. So conclusions and next steps. So we already have the first version of our MLPPA pipeline running. It has been released, and it was successfully tested on available data. Right now, we are starting to test it with the data coming from the new generation of radio telescope, MeerKAT, which one of the precursors of the SKA that I've mentioned. We also work on improving it in different ways. So one way we are improving the digital twin, adding different features to improve the model of the pulsar, of the interstellar medium, and so on. The biggest problem at this moment is the low signal to noise behavior, because at the low levels of signal, the expert system gets confused. So we apply different additional methods to improve this behavior. Well, and this is it. Thank you.
Thank you, Yuri. Do you have questions for Yuri for this part? As usual, you can use the chat or the Q&A, which you can do also after. But if there are no questions, you will move to the last presentation from Javad, and we're gonna be a little bit late than planned, but hopefully 5 minutes more. Thank you. Thanks a lot, Yuri.
Hi, everyone. My name is Javad Kamijani. I work at ETH, and I'm going to present a use case for lattice QCD. Okay, let me start with the introduction about the standard model of particle physics. The standard model of particle physics incorporates almost all we know about subatomic physics. This model is basically a set of quantum field theories describing 3 of the 4 known fundamental forces: electromagnetic, weak, and strong nuclear interactions. And also, it classifies all known elementary particles, including quarks and leptons that you see in the lower right panel, and also the Higgs boson. What we do in lattice QCD is we calculate the parameters of the standard model in order to search for unknown physics. This is done by comparing the results from lattice QCD with experimental results measured at physics labs like CERN. To calculate the parameters of the standard model, we of course need to solve the quantum field theories. Quantum chromodynamics is actually the most difficult part. It is a theory that describes the strong nuclear interaction between quarks and gluons. And it is notoriously difficult because it is highly nonlinear, and it is not possible to use analytical methods to calculate it accurately. So what we do in lattice QCD, we use numerical methods. This method is based on the path integral formulation of quantum field theories. Let me just say that in this formulation, we basically consider all paths that one particle can go from one point to another point, and then we integrate over all of these paths. So in principle, this method involves extremely high dimensional integrations, which is not possible to do it exactly and even numerically. So we rely on statistical methods like Markov chain Monte Carlo simulations to do the calculations. Even with this methods, we have to do the simulations at different resolutions. For instance, here you see 3 different resolutions. We have to do the calculations at different resolutions and then extrapolate the results to infinite resolution. And this is what we do in lattice QCD. And although lattice QCD has been extremely successful, it becomes a bit slow, and also it suffers from high correlation times as the resolution of simulation increases. So it requires presenting new methods. Okay, for instance, here I have, in this graph, you see a set of ensembles that are generated by collaboration, the MIL collaboration. It takes several years to generate these many ensembles with different resolutions. The horizontal axis is basically is a proxy for different resolution, and the vertical axis is a proxy for different values of, for instance, 1 quark mass. So in principle, one needs to generate these many number of ensembles. And it is also extremely difficult to save and transfer these ensembles of field configurations. So the focus points of our use case here is to use the power of machine learning-based generative models to generate field configurations for lattice QCD with different parameters and resolutions. So replacing the traditional methods with the machine learning-based generative models. And also the hope is that once we can develop such models, we can save and transfer the trained models rather than the field configurations, which are extremely expensive and heavy. Okay, what we use in this package, we actually use the method of normalizing flows to generate samples. We use a method that is based on self-training. Rather, we don't need external data to train the model. So the way it works with the method of normalizing flow and the self-training is that we start from a set of prior distribution as shown in this diagram. And then we basically we find a neural network that maps the prior distribution to a target distribution. And then we optimize the loss function that depends on the so-called action of the theory. Basically, each theory has an action that describes the theory. Given the action, you know the theory. So in this block diagram, you can see that we start from the prior distribution, we transform them, then we weight them according to the action, and we construct the loss function and we optimize. So in this, the proof of principles for these kind of calculations are already done for very models, and we are using that. However, there is a point that these kind of models are not necessarily as efficient as we hope, at least at this level. So it is important to combine these models with other methods like the conventional Markov chain Monte Carlo simulations. And we also do that in the generative block of this block diagram. You can see that we have combined the method of normalizing flow with a layer of accept reject step to improve the efficiency. All right. So for the method of normalizing flows, we actually need three essential components: a prior distribution, a neural network to map the samples, and also the action that describes theory. This package that we have has a high-level class that is called model, and in this code block that you see here, it schematically shows how we create a model by creating an action, prior, and network, and passing it to the model. And the model then is equipped with methods like fit. We try to use the terminology of scikit-learn, which uses for instance, fit instead of train. And we use the method called fit to basically train the model. Once the model is trained, the model has other methods to merge the output of the model with other methods, like applying an accept reject step. In this package, we have already several coupling layers or several transformation neural networks, several neural networks to transform the scalar theory. We have, for instance, coupling layers with affine transformations that you see in the lower right panel. And also we have coupling layers with rational quadratic splines. We have layers with power spectral density flow and so on. And putting them together, we can basically simulate scalar theories. Okay, what I said so far is more related to scalar theories. One of the main difficulties that we have is the mathematical objects that we are dealing with. Here in lattice QCD, the main mathematical objects are the so-called gauge links. Each link is a 3x3 matrix, a spatial unitary matrix. And this makes it very difficult because the gauge links satisfy a huge class of symmetries that are called gauge symmetries. So the main difficulty right now is to design flexible neural networks that respect the gauge symmetry. Respecting the gauge symmetry is very crucial in building and training efficient models. Okay, so I try to be a little bit fast because I think we are going a little bit, we are running out of time. So let me just give the concluding remarks. So far, we have a package that is able to simulate scalar theories with the current neural networks that it has. We are working towards including strong nuclear interaction. And right now we have a class of novel neural networks that are explored, and we are going to add that to the package. In the next step, we need to continue on developing new classes and also combining the method of normalizing flow with other methods in order to improve the efficiency, especially at high resolutions. And the hope is that after this step is finished, we can basically perform a precise research by integrating this package with highly optimized lattice codes. That, for instance, there is an OpenQStarD code that is highly optimized, and we can basically combine our package with that code in order to perform precise research. Okay, thank you so much.
Thank you, Javad. Thanks a lot. I don't see questions on the QA. I don't know if there are questions that you want to chat or We ran a little bit late, not so much at the end. But if you don't have questions, yeah, I think that we can close the webinar then. And thanks, of course, all the speakers and for participating. Just wanted to mention that we will organize also new webinars after the summer. And this time we will concentrate on the technology of the digital twin engine that we are building, particular technology. We will share this information on newsletter and social media. Thanks again to everyone, and we speak on the next webinar.